All right, so we basically covered now the top half of this page on electrical potential energy and electric potential. We've shown how to go from the source charge to the electric potential for point charges. Most important is to memorize what a volt is, joules per coulomb. And here's our intuitive definitions. The voltage indicates what the energy would be for a positive 1 coulomb charge. And the energy indicates how much work it would take to move from infinity to that point. So these are good things to study. And here's what we learned about the interpretation of potential. For positive charges, potential is like height. And for negative charges, potential is like, maybe I should have called it lowness. Okay. All right. However, for many problems, what we care about is not the energy, but the change in energy. Well, we already saw how to think about that when we talked about gravity. Remember I talked about moving from a low table to a high table. Well, then the change in your energy would tell you how much work it takes to move from one place to another place. So we can do the same thing over here. And you can see this is the bottom half of that same page of the handout. How do we relate potential, delta V and delta U? Now this would be called the change in energy. And now this would be called the electric potential difference, for obvious reasons. Sometimes this is called the voltage as well. For example, let's say that we move a charge from this plate of a capacitor to this plate. And let's say that the change in its energy is 3 joules. What would that tell you about what happened here? Well, first of all, did the charge here get happier or less happy?
Less happy.
Right, because its energy is increasing. Nothing wants to increase energy, so we had to do work to move it up here. How much work did we have to do to move it from here to here?
3 joules.
Well, that's a common type of question you might see. How much work does it take to move a point between 2 points? Again, usually we don't care about infinity. We care about 2 points in space. That's why we deal with delta U a lot more than just U. On the other hand, then, what do you think the energy would be, the change in energy would be for the same particle that moves from the top to the bottom? If the energy from here to here was positive 3 joules, what should be the energy change for going from here to here?
-3.
This is negative, which indicates the particle is getting happier. So we don't need to do work to move it from here to here. It wants to move here. So how would we interpret this? Well, a common question would be, how fast is this particle going to be moving by the time it gets down to here? Well, how could you figure out how fast it was moving by the time it got down to here?
Well, you know, its kinetic energy will be 3 joules.
That's right. It's losing 3 joules of potential energy, but energy can't just disappear. That must be going into its kinetic energy. Of course, we're assuming that it started at rest. If we assume that it started at rest and it loses 3 joules of potential energy, then at this point the kinetic energy would be 3 joules. And then if they told you the mass, you could solve for the velocity. Right. So, okay, so those are common types of problems. If a particle is moving where it doesn't want to move, then the energy tells you how much work it's taking. The change in energy tells you how much work that takes. And if the particle is moving to where it's happier, then it should be speeding up. And then the change in energy can be used to figure out how fast it's going. And again, those are pretty common types of questions. We know that U equals V times Q naught. So what do you think is the relationship between delta U and delta V? It's a very similar formula. If the level of U is proportional to the level of V, then we can use a similar formula for the deltas. And again, you're going to use this formula a lot more than the previous one, because the previous formula is really comparing a point in space to infinity, which doesn't come up too much. You're much more likely to compare 2 actual points in space. Again, I'm not putting dots in here because we want to put in the correct signs here to see whether things come out to be positive or negative. Let's go back to a capacitor again. We haven't talked much about a capacitor, but a capacitor is a device that has a separation of charges. We might talk about the potential difference for that capacitor. and that might be something, say, 5 volts, 5 joules per coulomb. It doesn't really make much difference. We shouldn't worry about the sign too much here, because obviously the potential difference is positive in one direction and negative in the other. So all we're really focusing on here is the magnitude of the potential difference. What does this tell us about this capacitor? If there's a potential difference of 5 joules per coulomb between these two plates, what does that tell us about the capacitor? How do we interpret 5 joules per coulomb?
Like in terms of for one coulomb charge kind of thing?
Exactly. Good. We put in the number 1. So what does it tell us about a 1 coulomb charge?
There is a change in potential of 5 joules.
A change in potential energy.
Energy.
Remember, we don't want to confuse energy and potential. The change in potential is 5 joules per coulomb. So this tells us, so suppose that we...
Isn't that a delta V right there?
This is delta V?
Uh-huh.
Yeah, that's right. The potential difference here is 5 joules per coulomb. And we want to interpret that in terms of what it tells us about the energy of a 1 coulomb charge. Because remember, the units for V are joules per coulomb, but joules are the units for delta U. So this can tell us, and coulombs are the units for charge. So we can interpret joules per coulomb in terms of what it tells us about the delta U for a 1 coulomb charge. So for example, let's say that I put a positive 1 coulomb charge over here. Well, it likes it over here because it's close to the negatives. I'd have to do work to move it up here. I'd have to increase its potential energy. Well, how much energy would it gain going from here to here? 5 joules. So this is the most important concept that we're just getting to at the end. The potential difference between 2 points tells you how much the energy of a 1 coulomb charge would change, moving between those points. Which also tells you how much work it takes to move a 1 coulomb charge between those points. Or how about if I let the 1 coulomb charge fall from here to here? Well, then it would lose 5 joules of potential energy, which would go into 5 joules of kinetic energy, which we could, as usual, use to figure out how fast it would be going. So suppose that instead I've got a 2 coulomb charge. What would its change in energy be if I take it from this plate to this plate?
10 joules.
Yeah, there's 5 joules for 1 coulomb. There must be 10 joules, positive 10 joules for 2 coulombs. That should be obvious, but you could get that from this formula. Delta V times Q equals delta U. So that would mean that it would take 10 joules of work to move a 2 coulomb charge between here and here. Well, that makes sense. The bigger the charge, the less it likes moving up here, and the more work it takes. But you can see why it's so useful to know the potential. A capacitor might have many different charges moving between them. You don't know ahead of time what types of test charges you're going to be focusing on, but if you simply write down as the potential difference how much the energy change would be for a 1 coulomb charge, then it's very easy to translate that into any particular amount of energy that's changing. All right, so what we started going over here was down the bottom of this page on potential difference. Unfortunately, we didn't get too much time to talk about the left-hand arrow over here, but we talked about how to go between delta V and delta U. And we talked about the intuition here. The delta V between 2 points indicates what the delta U would be for a positive 1 coulomb charge. And so we didn't quite talk about this, but notice that for positive test charges, delta V indicates the change in your height. But for negative test charges, delta V would indicate the change in your depth. So notice that these positive charges don't like moving up here, because, so this must be because they're increasing their potential. A negative charge would like moving here because for a negative charge, this would be the this would have a greater lowness rather than the greater highness. Okay.
Okay, great.
All right. So one thing to work on before we meet again is thinking about the units. We reviewed the units for field, for force, for energy, and potential. So those are all good things to try not to get confused. In particular, a volt is a joule per coulomb. All right, so hang on to that handout and keep bringing that with you to the sessions. In fact, also, it would be, I would recommend just sitting down and studying that handout and kind of thinking about the relationships, because those are all really important pieces of information.
Okay, I'll do that.
These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you.